This conference will now be recorded.
Yeah, hello everyone. So we'll be doing the PCIe physical layer RTL coding and SV-UVM based test bench development demo session now. So as part of this session, we will be understanding the what all aspects we are going to cover as part of this course. So basically, it will be a course that will go for around a total of 25 hours duration, and initially we'll be doing RTL and test bench development in parallel. Okay, means while we are developing the RTL code, concurrently we'll be developing the test bench. So this will give you a good exposure. I mean, if you see PCIe physical layer can be divided into two parts. One is the logical block, logical subblock, and one is electrical subblock. So very at very abstract level, the logical block is the digital part of the implementation, digital part of file layer, I mean physical layer. Okay. And if you see electrical subblock is the analog part of the uh, physical layer kind of, because physical layer has two aspects. One is physical, logical, and one is physical. Okay, physical layer. Mostly our project will be, I mean, whatever we are going to will be focused on this. We will be focused on the logical subblock implementation, which would in turn consist of various aspects like LTSM. Majorly, it consists of LTSM, and because remaining all the things are implemented into electrical subblocks. It could be, say, we are talking about doing the 8-bit NB encoding, even the this thing, or do you say scrambling? Most of it gets implemented into electrical subblock. So we'll be implementing the logical subblock, that is the LTSM portion of the C Express. I might be a bit wrong here, but if it is applicable to logical subblock, we will do this as well. Okay. So this is what I mean. This let me correct and get back to you. Okay. Transmitting and receiving of the signals. We won't be doing at the analog level. Rather, we'll be focusing at logical subblock. Now, coming back to the our focus, I mean, what would be the plan? So we would be basically working on the first one aspect of the course will be focused on RTL coding. So we'll start off with listing down the physical layer features. We'll come up with a top level architecture. Then we'll come up with micro architecture. We'll list down the interfaces. What all interfaces does physical layer has? Then we'll be listing down some of the registers that goes into physical layer. Then more importantly, the most important thing, we'll come up with a state mission for the physical layer implementation. Then we'll be talking about, we will be implementing the subblocks RTL coding. Essentially, we'll be implementing the RTL coding using this FSM. Then, I mean, if required, we'll do the integration. Otherwise, we'll just develop whole physical layer RTL as a one unit. So once, while we are doing that, parallel to this, we'll be doing this activity where we'll come up with a system verilog and UVM based test bench development, architecture, test plan, developing the test bench component, integration of test bench component, running the test case and debugging and setting up the regression. So these all aspects we'll be doing. And this, if you ask me, is it possible to do it in 25 hours? It is quite possible because I have done a similar complexity. Like, see, earlier I have done the PCI Express transaction layer and data link layer. At least transaction layer currently I have done in around 25 hours. We were able to complete the most of the activity related to transaction layer. Though of course the RTL code will not be as standard as any product company designs, but still you will be able to see the transactions happening, the packets going through the interface, all those things. So we will be able to achieve that level of uh, coding in terms of the design and test bench. Okay, now let us directly jump into the course and let's see how we can come up with this flow. Okay. So if you see, let's directly start off with the architecture of the physical layer. So if I start off with physical layer architecture, if this is my physical layer, I'm only talking about the logical subblock. Can you tell me what all interfaces does it has? What all interface does it has? It has got, on one side it has got a DLL block. On one side it has got a DLL block. On one side it has got a pipe. So this is the DLL. On the other side you have got a pipe. So pipe stands for what? Phi interface for PCI Express. DLL is the data link layer. So with data link layer, it has got two directional interfacing. What is the two directional interfacing? One is the receive path, one is the transmit path. So here, same thing. On this side, it has got, sorry, one transmit interface to the pipe, one receive interface from the pipe. So this is the DUT for us. So we are going to develop this DUT as well. Again, if you ask me, is it possible to develop this DUT? So many things in this much duration. It is possible. I just want to show you so that you get the confidence as well. Uh, so it will be done over the server. Uh, so it's like say, so here we have developed one test case where uh, we are doing PCIe memory write test. Basically, this is a memory read, write, and read test. So in this case, what we are doing is this is the test case which we have targeted for transaction layer. So we have developed uh, the this one PCI TL. So we have developed the RTL code. This is around close to 900 lines. So as part of that, we have developed the transaction layer RTL code. It has got various states which we implemented. The state machine related to the processor interface, state machine related to the DLL interface, state machine related to the memory interface. Basically, there are three interfaces in transaction layer. So corresponding to that, we have developed and we have developed the entire RTL code. And parallelly, we have developed this entire test bench, the one you can see here. Go down, we have developed various components, DLL, RX, TX path, memory path, scoreboard, AXI. I think this currently we are at only 18 hours. Only we have done 18 hours of lecture, only 18 or 17 hours. So we are able to develop a properly working code. Now, you may ask, what are you trying to do here? I mean, I'm trying to give you a confidence that 25 hours would be sufficient for us to complete the physical layer project as well. So here we were able to generate the transactions happening. So on the DLL interface, we were able to generate the packets and see, this is the interface, TLDLL interface. We were able to send the TLPs, and we were able to generate a memory read request. So here what we have done is uh, we have done a memory write. The same data is being read. We have, so this was memory write, and then we did a memory read. Then we are getting back a completion packet. So we could even verify. So whatever data that is coming as part of the memory read, we were able to write it into the memory through AXI interface. So we are able to perform a write into the memory. So these all things we have validated by running the simulation. So it is to just to give you confidence that 25 hours is not a very short duration. We can do a lot of things in the 25 hours. So we will be able to confidently, properly complete the PCI Express transaction layer design and test bench development in 25 hours. Of course, one thing we need to notice is if you go to the companies like Synopsys, who develops these IPs, let's say Synopsys develops PCI Express physical layer VIP, maybe, or PCI Express VIP. They have 5 to 6 people working for 1 year, 1 full year, and developing these IPs. So we won't be able to match that level, right? Because the kind of fine control, the finer level of coding they do at each stage, we cannot do in 25 hours. But we can still reach a stage where you understand how the things are happening, how the the physical layer interfaces with the other DLL, how it interfaces with the other device at the other endpoint. All those things we will be definitely able to implement as part of these sessions. Okay, so coming back to our flow, so what we are going to do is this. So I think we were looking into the this one. So if you see here, it has got majorly two interfaces. Though we haven't shown here, there are one more interface will be present here. Actually, there will be one memory present here. Actually, there will be a memory present because whatever, how does what does physical layer does? Physical layer will be sending the two types of packets. Can someone tell me what are the two types of packets physical data link layer will be sending to the physical layer? One is called as link packet. One is the orders. No, sorry, DLLPs, link packets and DLLPs. So what this physical layer does with that? It does the framing of framing of link packet. Means what is meant by framing? It adds STP, STP, END, EDB based on what type of packet is it. It will do that. Other than that, what else physical layer does? Physical layer also generates its own packets, generates order sets for link training. Majorly, most importantly, it has got an LTL system implemented into it. On this side, it will be receiving three types of packet from the pipe interface. It will be receiving three types of packet. What are the three types of packets it will be receiving? It will be receiving the order sets, the physical layer packet, and DLLPs. It will be receiving all these packets from this interface. So what it does, order sets it will consume for order sets used for link training. uh, Physical layer packet and DLLP, it will forward to DLLP, DLL layer. Okay. Here, it will be sending again the same packets, the link packet and DLL. Now, what is happening is whatever packets that are coming here, the same packets are transmitted here. The link packet is being converted to physical layer packet. So PLP and DLLPs and order sets are transmitted here. So in between whatever packets that are coming here, they need to be buffered. There will be a, I mean, we may have to either buffer them. See, if the buffering is required, we may use this buffer. So the, if we can call it as SRAM buffer, what it is going to do is whatever packets that are coming into it, we will buffer them into this one. So there will be one AXI interface through which we may buffer. If required, we'll do that buffer. Or if we go for on the fly processing, what is meant by on the fly processing? As the link packet keeps coming, you keep you update it to PLP and keep parallelly transmitting it. In those cases, you don't require the SRAM buffer. So we'll decide how to implement this part. Okay. Now, many times this is very much specific to how we want to implement it. Then finally, what we will have is we'll have one block here, which will be uh, we will call it as a scoreboard. So what is scoreboard is going to do is this will be, because for us this is the DUT, we will implement it as the DLL UVC. Since we are doing in UVM, we'll call it as the UVC. We'll call it as the pipe UVC. Okay. And this instead of SRAM buffer, we'll call it as SRAM UVC, memory UVC basically. Each UVC will have a memory, if you understand. See, monitor. So here there will be a monitor. There will be a monitor for this UVC. Okay. There will be monitor of, if at all I implement these things as two different components. Let's say if I implement this as two different components, what is mean by that? Let's say I call it as DLL transmit UVC. I call it as DLL receive UVC. So there will be one monitor here and there will be one monitor here. There will be monitors both the places, and there will be a monitor here also, and there will be a monitor here also. All these monitors finally will get connected to this one. This one also gets connected. So all the monitors will get connected through the analysis port and implementation ports, and internally scoreboard will handle these packets. How the, I mean, this will also go here. So all five connections will come here and the scoreboard will handle it. That is something we will see how to implement the scoreboard. So this is the top level architecture, what we are going to do as part of this project. Do you have any questions till this point?
Sir, one question. That the right side, the DLLP is there, right, sir?
Your voice is not clear.
Hello? Sir, is it okay now?
Okay, but kind of here. Yeah, please tell me.
Hello? Sir, is it
Yeah,
audible
now
now?
it's, yeah.
The right side DLLP is there, right? Usually there will be two packets to the physical layer. One is link packet and another is DLLP. But from the pipe UVC, the DLLP is called as DLLP only. That also will be coming with this that start and the end. We will add some bits, sir. That it will also come with that bits, right?
Yes, it will come with those bits.
Then
No,
that
yeah, it
all
will
is
come. Yeah, the physical layer once it receives, it will remove those start and end symbols, framing symbols, and it will send the DLL.
but the name convention is same as DLLP only.
Yeah, name convention is same. Yeah.
Oh, okay.
Only transaction layer packet has a different naming convention. When it comes to DLL, it becomes link packet. When it goes to physical layer, it becomes physical layer packet. DLLP remains same.
Oh, okay, sir. Okay, sir.
Okay, so this is all we will be doing as part of the project. Any other questions? Okay, so if you don't have any other questions, we will directly start off with the uh, project itself. So There are two things, design and test bench. We need a design. Now you may say, why don't we use a design from somewhere? I mean, why don't we get design? It's not easy to get the design. I mean, even if you go to some Google and just search PCI Express physical layer RTL code, it's probably not so easy to get. You won't get it actually because these are proprietary materials. So the companies won't release those codes. That's the reason we are developing our own RTL code. And see, we do have some level of expertise, right? It's not like we have to get everything from somewhere. So that is where we are developing our own RTL code. Our idea is to what is the whole final goal of this project is to get familiar with the PCIe physical layer from a practical user's perspective. I mean, at the end of this course, you'd have understood how physical layer interfaces with the data link layer at both the transmit interface and receive interface. Then how physical layer logical subblock would interface with the pipe at transmit side, receive side. How it handles the incoming packets, how it handles the packets coming from the pipe. That level of your expertise you would have gained through the practical exposure. See, when you read the protocol or when you go through the protocol videos or you attend my training, you would have got theoretical exposure. This course will give you that practical exposure, and the fact that LTSM is one of the very important aspects of this physical layer. So when we implement LTSM for all the various states, including link training, recovery, hot reset, and the low power states, you would get a very good exposure to that entire flow. So that is the overall intention of this training. So I'm not telling that we are going to develop a big complex IP, we are going to become experts with the RTL coding, not like that. But second thing is you would have got good expertise with the UVM based test bench development. Reason is it has got multiple interfaces. If you see, it has got 5 interfaces. Sorry, one is this 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 one. So given that there are 5 interfaces and each of them can generate the packets. See, this can generate the packets. So because of this, of course, this won't generate the packets. This won't generate the packets. At least there are 2 complex interfaces which are going to generate the packets. You would get exposure to this kind of complex design test bench development. I mean, if this was a real design, it would have been actually complex. The similar level of complexity you are going to feel as part of our project. So the only thing I expect from your side is I want you to also do the things parallelly in parallel with me. What do I mean by that? Most of the time I have done these kind of projects, the PCI Express transaction layer, data link layer, physical layer, RTL and test bench development. The participants have been mute spectators. They have been just attend the sessions and see what I am doing. My observation is if you do that, you don't learn anything. You have to sit down and you have to start doing the things yourself. Unless you do that, you won't benefit out of the course, because even if you go through the lectures and even if you attend, you watch everything I do, even if you go through the code whatever I have developed, you won't learn anything. After 1 or 2 months, you would have only learned 10% of what I have actually taught. That 100% learning happens only if you do the things yourself. So that I want you to remember and do that without negligence on that part. Okay, so let me directly get into the test bench development and design and test bench development now. As we start developing the design and test bench, we will also talk about the features and everything, because I expect that the people who are attending this training have a good level of exposure to physical layer. So I don't want to again start off from the basics of the physical layer. So let us start off with the coding part. So if you see, I'm going to develop PCIe physical layer SV. See, this is how very much the transaction layer.sv also started. I mean, we started with the empty file and we started everything here. Now, the first thing you have to ask is the EL and module. What all interfaces are going to be there here? Physical layer will have what all interfaces? If you remember whatever I explained here, how many interfaces do you see here? There are totally 5 interfaces. One is the DLL transmit and receive interface. One is the pipe interface. Now you may say, it should it be pipe UVC? Actually speaking, this is going to represent everything on this side. So it's not just the pipe alone. It is going to represent, there will be some device, right? Finally, through the link, you would have connected some device at the other end. It is going to represent everything. But since I don't want to show everything, I'm just calling it as pipe UVC. Same thing here. It is going to represent not just DLL, it is going to represent the transaction layer also, because only if transaction layer is there, transaction layer packets will come, right? Otherwise, how will it come? So this represents everything on this side. This represents everything on this side. It's not just the pipe alone. So here also, it's not just DLL alone. It's transaction layer and the upper layer. Everything put together is what is represented here. Okay. So any questions so far? Okay. Now it has got, if you look at this, it has got DLL RX interface, DLL transmit interface, physical layer receive interface, physical layer transmit interface. Okay, if required, it is going to have a memory interface. Okay, these are the things it is going to have. So now let us start off with the DLL RX interface. How do you think DLL RX interface will look like? What do you think this will be? Will it be, sorry, if I go here, will it be AXI interface? Will it be APB interface? What kind of interface it will be? What kind of interface do you think it will be? It will not be any of those things. It will be a some kind of custom interface. Custom means what? Something that company has designed internally. Let's say it is Synopsys. Synopsys will decide what kind of interface do they want. It will be a simple interface. How it is going to look like is, it is going to have, this is transmit, right? So it is going to have a clock coming into it. DLL receive interface. Okay, a clock coming into it, that is DLL PL clock I, the clock that is coming into me. Then it is going to have DLL transmit data I, DLL transmit valid I, DLL transmit radio. So these are the simple. It's a very simple interface you see here. Transmit, transmit data. Mean what is that? The data that it's going to transmit. Okay, valid. And in response, I'll give ready and a clock on which this interface will happen. Other than that, here we'll use the same clock for both of them. We'll use the same clock. So if it is declared in the top, so this is down, it's not required. It is going to be RX, receive data O. O means what? It's the output of the my design. See, that data will go from here to here. This data is going, so it's an output. Okay, receive data. Then DLL RX, this will be RX valid. Again, we are sending out the data, so we are telling that this data what I'm sending is a valid, and RX ready in. This defines these two. And other than that, if you remember, in physical layer, the communication between data link layer and physical layer involves one more signal called as link up. I need to tell that link is up, right? Physical layer indicates to the data link layer that link is up. So that communication also we need to be sent. So we'll have one more signal called as link up O here. Have you understood what is the need? The physical layer uses this signal to indicate to the data link layer that now the link training is done, link is up. So what is, why data link layer will use this? This will use this signal to decide now the link is up. I can start sending the DLLP link packet to the physical layer. Do you have any questions related to these two things?
size will be, sir?
Sorry, please tell me.
The data size, sir, is it
It
32
will be
bit or
different.
64?
It'll be either, we can do whatever we want. We'll keep it 32-bit only. Okay.
Okay.
We can even keep it configurable. Okay. Next, going by the same thing at the physical layer RX IFC. If you go back to this diagram, this I'll call as RX interface. This is the transmit interface. This I'll call as what? Wait, receive interface. I have to follow some naming convention that is very important because otherwise we'll get confused. Transmit. So I will name it as transmit this also I'll call it as transmit UVC. Pipe transmit UVC. This I'll call as pipe RX receive UVC. That means what? Pipe transmit interface. This I'll call as pipe RX interface. Okay. So what all signal will be there at the transmit interface? Data that is coming out of it. So what is the data? What is that? Transmit interface, right? So first let's start with this. It is PLL PL pipe transmit data. Oh, correct, right? The, oh, sorry. PL transmit interface. Is that correct? Yeah. What else? PL pipe transmit data valid. Transmit valid O. PL pipe ready I. Similar to that, here also PL pipe RX data. See, wherever TX is there, change it to RX here in this line. And wherever I is there, change it to O. Change it to I. Change it to I. The data that is coming from the pipe. This is the data that is coming from the pipe. And pipe is telling that this data is valid. My physical layer is telling that I'm ready to accept the data. What will be this interface? That all those things let us define. I mean, at every time we'll keep checking whatever we are doing, is it in line with the PCI Express? How the data gets transmitted here? The data gets transmitted in a serial manner, right? No. It gets transmitted in a parallel manner only because the pipe is different concept. See, the pipe is if I go to internet and just search the PCIe pipe 5.2 specification. If you download it, let's see, anything you can download for that matter. Let's say you download this one. So on one side of the pipe, it is going to have, if you go down otherwise, you will see the, see all this portion, what is that? Uh, 8-bit NB encoding, decoding, 128B, 132B encoding, elasticity buffer, RX detection, everything we'll do it in the PCS, physical coding sublayer, which is, we are not going to do that part of it. Okay. I think what is this? It's not USB. It is, sorry, it's USB. That's the reason it's different. Yeah, this is the one. See that. See, 8-bit NB encoding, decoding, it can be in, as part of the pipe, it can be part of the SERDES only, depending upon whether you have implemented in SERDES or whether you implemented as a virginal pipe. For now, let's ignore this one. So these are the media access layer is what we are implementing. We are not implementing this. So this is the 5 MAC interface is what I'm calling as the pipe interface. This whole thing I'm calling as the pipe. Okay. So for us, what is that? This is our RTL code. Here we have a data link layer. Here we are interfacing with the PCS, that is physical coding sublayer. Okay. right? So for our convenience, we will not do any 8-bit NB encoding here. We'll keep it. See, there is an option where this can be done in the original pipe. So we'll keep it for physical coding sublayer only. So we'll do the remaining things as part of the media access layer. Any questions so far? Why we are looking at this nodes is we want to see how does this interface look like. If we go down, it will indicate how this interface will look like. This is the MAC layer. This is the file layer. That is the PCS we were talking, right? Uh, this is what we are going to define. So this interface is exactly is what our this interface is going to be. Understood, right? This I am calling as the MAC, media access control. This we are calling as the PCS, nothing but actual phi electrical block. Okay. Have you understood? This is the data link layer. If you can see, this is our DUT. So DUT sends the data in 32 bits. This is going to collect, it is going to convert the packet, and it's going to transmit as TX data. It can be any of these interfaces, either 64-bit, 32-bit, 16-bit, or 8-bit. It's up to us. For now, we'll keep it only 32 bits because we are not here to complicate the design. Our intention is to keep the things simple and understand the things better. Okay, so this is what we are going to do. So without wasting much time, let's see how these signals are defined. Understand, so we are not going to work at the individual lane level. That is the responsibility of the file layer. So we are going to implement it as a UVC. So this thing becomes internal to the UVC. We don't have to worry about this aspect. So how that interface signals are there, so we can see down. This is the one which we are looking at, the pipe interface signal description. So if you go down, you will be able to see this. See, there is a transmit data. Okay. It is applicable to PCI Express also. So you go here, and what else is there? Transmit data to transmit data valid. Do you see transmit data valid is there? Other than that, what else is there? Mostly that is on the transmit side. On the receive side, what else is there? Let's see. On the receive side, there will be receive data. Okay, you can see receive data, which is either 32-bit, 16-bit, 8-bit, depending upon what is the requirement. Then you have got there are some things like phi mode, DP mode. There are various other signals. Right now, I'm not going to consider them because my point is, as we require, we'll add those things. For now, we are going to keep the interface simple. If at all you want to add, we can add all these things. We can add this. We can add electric idle because it is applicable to PCI Express also. We can add this not applicable to PCI Express. Reset we can add. Power down we can add. So for now let's just define all of them. Whether to use them or not, let's decide later. So phi mode is applicable. So the phi mode. This will be at what interface? What is the direction of that? Phi mode is an input or output. Somewhere they would have written. Display port phi mode will be input to me basically. If it is input, it will be part of which interface? If it is input, it will be part of the receive interface. So here you can say I mode I. Then what else is there? This is related to display port only. Means it's not specific to PCI Express. Then SerDes architecture. It's input. Okay. Next, SRIS enable. Whether what is the direction, I don't know right now. We'll check that because they should have given the direction also. They haven't specified the direction, so we need to read this and figure out what is the direction of each of them. TX detect RX. It's a output of the design basically. This is not there. TX electrical idle. It's a output forces the transmit output electrical idle. TX electrical idle output. Since it is enable, let's also call it as output only. Next, reset is applicable. Reset underscore reset hash reset underscore o. And what else is there? Power down is there. Power down o. I mean the power down indication given. We what we have to do is to figure out whether it's input or output. You have to read this. See, it powers down the transmit transceiver or receiver means what? The upper layer is indicating to power down, so that means it's a input to the pipe, means output of my physical layer. It's output of Mac and input to the PCS layer. Okay, similarly like this you can write down all the signals. See, power down, this is not applicable. Short channel power control. See, these things you can add because right now I don't have any plan to use these things, so I'm not keeping them, but as required we can add those signals as well. See, transmit common mode disable. Transmit common mode disable underscore o means it's an output. Like this you can declare various signals. What is the transfer rate? I think mostly it captures the things, and what is the width also we can specify. Data part width, whether it's 8-bit, 16-bit or 32-bit, that can also be captured. uh, P clock rate can also be captured. Width underscore o. P clock rate underscore o. So it is capturing all the signals. Yeah. Oh, okay. They have given everything as input signals. Yes. You can see that in the top they're telling it's input signals. Means everything you see here is an output only. And our analysis was correct only. This was output. Phi mode is an output. These are all outputs. Okay, because you may ask, they are telling input. See, it is input to the pipe. Input to the pipe. Output of my physical layer. Output of physical layer. Input to the pipe. Input to the PCS. That's why for me everything is output. Now if you go down, there is a output signals also. Down if you go, output signals. Ref clock required is an input for me. Okay, RX standby status is an input to me. So these things can be declared. Ref clock required is an input. Clock required is an input. What else? RX standby status. RX standby status. It's an input. And what else? I think the remaining things we RX valid we have discussed. RX valid is required. Phi status can be one of the things that comes. RX electrical idle, and these are all what output signal means. For me they are input. Phi status is an input. Okay, what is the next one? RX electrical idle. RX electrical idle is an input. What else is there? RX status. RX status is there for PCI Express. Yes, RX status is there. So that can also be again one more signal. Then what else is there? Power present is only for USB, P clock change, okay. So all these things, yeah, I think it kind of completes all the signals. So this is what I may have missed one or two signals. Thing is, this is how you list down all the things and come up with the interface definition. Now whether memory interface is required or not, we'll decide later. So if required, we'll add it. As of now, let's keep it to do. I mean, only if it is required, we'll keep it. As of now, not required. So, any questions till this point? Have you understood what we have done so far?
Yes, sir.
Yeah, any, okay. So, now with this understanding, we have to define these signals. See, the point I am trying to tell is, even I don't have any interest in developing this RTL code, really speaking. If someone gives me this RTL code, I would be very happy to take that RTL code and set up the entire test bench and do the verification. But I don't have this RTL code. Without having this kind of code, I cannot do a verification. I cannot take an empty file and I cannot set up a test bench and do the verification. So hence we are developing this physical layer code. So parallelly, you will also gain a good exposure to how to develop the RTL code also, because this is going to have a complex state machine called as LTSSM. So how the LTSM gets implemented, how the state machine gets verified by the test bench, all those things you will learn as part of this course. So now with this understanding, let us declare the signals. So all you have to do is just copy paste these lines, these things. Input. Now you may say, is everything input? No, I'm just still in developing the code. So what I'm going to do is I will search for comma and I will do the things in an easy manner. I think I made a mistake. Done. Okay. So once you have defined it, it's an input. Underscore I means it's an input. Underscore O means it's an output. This is an input. This is an output. This is an output. This is an output. I mean, we'll change everything. You may be thinking some of them you're not changing. We'll do everything. Output. And what else? Now what we will do is we'll just look for the things wherever. Just go to input. So this is output. This is output. This is fine. This is fine. This is fine. This is output. These are all outputs only. Out, output, output, input, and input. These are all looks fine. Now let's review again. Let's search for outputs. Output, 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 output. So the next thing I'm going to do is I'm going to declare the dimensions, the vector sizes. So Rx data is 31 down to 0. This Tx data is also 31 down to 0. This is also 31 down to 0. X data, Rx data, PLL pipe Rx data. Similar to this, it's also 31 down to 0. Okay. Now, as for the other signals are concerned, I have to go to the this one, phi mode. What is the size of phi mode? You go to the pipe interface. Up. Phi mode is what? 3 down to 0. 3 down to 0. SerDes architecture is 1 bit only. It's only 1 bit. SRSI enable, it is 1 bit only, that we know because they haven't declared any dimensions. Transmit detect, this also 1 bit only, 1 bit. Power down is maybe more bits. We can go down, you can check. What is power down? It's 3 down to 0. So declare here 3 down to 0. Next, power down SATA. What is the next things we have got? Uh, Transmit common mode disable. Transmit common mode disable is 1 bit only. Okay. The next thing is rate. Rate will be multiple bits, right? Because rate can be multiple things. So rate is 3 down to 0. Next. Width. Width also is multiple bits. I think it's 2 bit. 1 down to 0. So width is 1 down to 0. P clock rate is also definitely multiple bits only. It is 4 down to 0. Next. Yeah, I think it takes care of all the signals. Now you may say you haven't declared some of the signals. The point is we are not here to implement every part of the physical layer, and it is not practical to do in the limited duration we are doing. We are going to complete around 70 to 80% of the major part of the physical layer implementation. 20% or 10 to 20% definitely we are not going to do because of the time limitations. So hence I haven't listed some of the signals because I know that I'm not going to use them at all. So if you ask me, are you going to use this signal anytime? Some signal I missed uh, somewhere in the top. Let's say short channel power control. I'm not going to use it because it goes into power control and everything, which I'm not going to do in this project. Okay, now that you have declared the dimensions, we have to actually the backbone of any RTL code is the state machines. Actually, we have to implement state machines. One primary state machine will be LTSS. Definitely, this design requires LTSS, uh, which tells the physical layer status. It is the status of the physical layer at any time. It indicates the status, indicates the state of the physical layer at any time. It can be in detect state, it can be in configuration state, it can be in recovery state, but it is going to tell me what is the state. Okay, so this is the part of the RTL development. Now, parallelly, I'm going to develop the test bench where I'm going to define the structure like this. Make dir top module, the physical layer UVC. Then what else do you have? DLL UVC simulation window, then scoreboard. Mostly these things will take care of it. So you go to the top.sv, top tb.sv. This is the test bench for us. So what is that you do as part of the UVM package.sv? Include, import UVM package star. Then of course you have a normal steps, right? Module top tb and module. What do you do? Very first thing I'm going to do is I'm just going to instantiate this interface by number 1 to 15, y14. I'm going to paste it. I'm going to call this as a dut, and I'm going to define these interfaces. Whatever I just now used, I'm just going to define interface, and I'm going to connect all these interfaces. So first interface is what? DLL, PL, DLL, PL, RX interface, intf. You can call it as DLL, PL. Sorry, this is RX, right? First one was RX. RX, PIF. Okay. One is transmit interface. So I'm going to define this, and I'm going to declare these interfaces. Let's say if I declare one of these, this will be part of TB, DLL, UVC, DLL, PL, RX interface, SV. Basically, we are going to do all these things from scratch. I'm not going to take any existing code and do, let's say this one. This corresponds to that, right? Uh, wait, the link up is part of what? Link up is part of link up is part of the receive interface only. Okay, so that means y4 interface DLL PL. Oh, sorry, it was supposed to be RX interface. Okay, this RX interface, end interface. You know that this clock will go into it. The clock would not go into it because the clock will be internal signal, because it's an output of the data link layer input to the physical layer, so it won't be here. Okay, bit, 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 bit. And the other thing is I'm going to save it as PB DLL UVC DLL PL RX interface dot sv. Okay. Okay, TX interface I need to change it. Then I have to change these things. So for that, again, you can go here, copy these signals, Y, P, these things. And clock is required here also. I mean, clock has to be part of this interface also. So RX interface. The clock is common to both interface. If at all you want to reduce the complexity, if at all we want to reduce the complexity, what I can do is I can just pull these signals into the same interface and just keep it here, call it as bit, and keep it one interface only. Instead of this, we'll name it as, because no point defining so many interfaces, DLUVC, DLL, PL interface. That's all. I'm not just going to name it as this alone. Okay. Now I will go there and remove those two interfaces. And remove those two interfaces. So here also I need to remove only one interface. I'll keep. I'll call it as just this one, physical interface. Now the things are simpler here. What I can do is I just need to connect those things. As you know, how do you connect them? So with this understanding, I can just do the connections. And these will have a different interface name. We'll do that. So this interface name will be different for these things. These. Okay. Are we missing something here? Transmit data, valid and ready. Yeah, this is also correct. And now coming here, this interface name will be different here. This will become BL PL pipe interface, pipe PIF. Only thing is this, I haven't declared this interface. So it's not going to work. So for now, I'm just going to comment out this. When I define this interface, I can just declare it quickly because anyway, let's do it. Testbench, the PLUVC, PLUVC, PL pipe interface, PL pipe interface.sv. So here I'm going to copy, you can declare the interface, PL pipe interface, end interface. So what all things need to be declared inside that? You just start from here, starting from line number 21, copy till 40, my 19. Just declare everything to bit. Just declare all outputs to everything changed. Now I can even declare that PL pipe interface, declare as PL pipe physical interface. Now since that I have declared these two interfaces, I need to include those things. Include the PL pipe interface.sv. Include the what is the other one? DLL PL interface. Now I can run the compilation. So to run this, I'll go to the TB sim run.do. Again, I don't want to do everything from scratch. I will copy the thing. I will do that for now. Blog, what is that I want to compile? Top tb.sv. Here we already have this project PCIe L TB TB sim run.do. I'll just copy a lot of things from here. Top, I have to include, I'm including the UVM source code top. What else I have to include? The PL UVC, because that is where my interface is present. Then DLL UVC, then the scoreboard. Mostly this takes care of all the things. Then I don't need line number 1. This is compilation. Then comes the, so once the compilation is done, let's run this now once. Okay, top TB didn't find. So what to do if top TB didn't find? So what I have to do is I have to give the top TB path. Top TB. there is one error, line number 19. There is a problem in the PL pipe interface. I think I understand what is the problem. The problem is with in the design. If you go in the in the where is it? I forgot. PL pipe interface. PL pipe interface. Line number 19. Okay, this I haven't not to semicolon. Same problem will come in the DUT also, right? Because DUT also will have here. This should be semicolon. Of course, what we do here, we sim hyphen no we opt. There is a specific syntax we have to follow because we are running with Questa sim. So syntax we are going to follow. Sorry, what I have done is I have copied the steps from here. I have edited the file to make it PL based test, and I'm elaborating here, commenting it out because these files are not there, and I'm running the script, running the thing. And there is a problem here where physical layer PL is failed. So it is because why it failed is it is because we didn't include that file. If you go to the top TB, we have to include that file also, right? The PCIe PL. And we in the run.do I have to include that path also where the RTL is present. Where is it present? One folder down in the design it's present. Right? If you go here, one folder back, in the design it's present there. Yeah, undefined variable RX status. See, now we are getting the errors related to the RTL code. Let's fix those things. Line number 10, there is a problem. Line number 10. This is not declared at all. Ref clock required I is not declared at all. Where is it? It should be after P clock rate. So ref clock. So it's a input. It's a input, so it should be only one bit variable. I think looks like this whole thing is not declared at all. Input. Input. RX status also let's declare as input only. Now I can just go and declare the signal sizes. RX status, right? Here also let's declare as underscore I. Next, I can copy these signals. See these 5 signals I haven't declared in the interface also. So here declare them as bit. Now I can run them and let's see. I think there are another error. One last error. The DLPL interface failed. Why it failed? DLL-PL interface. Is there any error before that? No error. Maybe we include is the problem. Let's go to top. DLL, sorry. This is there. It is there. So where is it present? TB, DLL, UVC, DLL, PL interface. It is present. If it is present there, if I go here, DLL, UVC, ELL, UVC. What would be the problem here if this is the case? VLOG, top TB. A instantiation of DL design unit was not found. Why it is not found? Maybe I didn't change the. I have to define the interface name properly. I got it. Testbench, DLL UVC, DLL PL UVC. See here I didn't change the name. That's the reason. Okay. PL pipe RX status, unresolved reference to RX status. Okay. So somewhere there is a RX status. Okay. In the top, it will be the problem. RX is underscore I is underscore I. That's now the compilation is clean and it is running. So basically it has run. So uh, so this is where we stop the session. In the next session, we will parallelly, as we said, we will parallelly develop the RTL code and we'll parallelly develop this code. See, we will be starting with this one where I'm going to start off with generating the link packets and DLLPs. So initially DLLPs will be sent because I need to do the flow control. So when I get the flow control packets, what my physical layer is going to do. And if you see, even before that, what is that? I have to do the LTSSM link training, right? So that logical steps we are going to do. Okay, so we are going to list down what all things physical layer is supposed to do. So we will be implementing them step by step as part of our physical layer RTL code, and then parallelly we'll be developing these components as well. Okay, so this is the brief about the what is the plan. So any questions you have? Okay, so we'll stop the session here. So we'll continue as you enroll for the course. We'll continue. I'll give you the schedule for the course and we'll continue further. Okay, so we'll stop here.